This is the first video over Chapter 10 of our AP review. We'll go over the multiple choice section here. I'm going to skip down directly to number 6, 7, and 8. And in this set of questions, we've got a bunch of flasks with a bunch of different amounts of gas. Notice we have 5 flasks rather. And we're asked about the properties. Now, this one notices 30 degrees Celsius, 50, 40, 50, 40. And this is a varied pressure. As just a quick note, remember PV equals nRT summarizes the relationship between pressure, temperature, and all these variables. If you have a high pressure system, that means you have a lot of gas in there. That's kind of one of the ways to create a lot of pressure is to put a lot of gas. If you see this at 2 atmospheres, that means we have a lot of gas in here. If you have a high temperature, that means the gas can also create a pretty high pressure, but the pressure, remember, will have to double in order, or the temperature would have to double in order for you to double the pressure. So let's see if we can get our heads around some of these questions. Number 6 says, in which flask do the molecules have the greatest average speed? Now, speed is connected to temperature. Remember, temperature is the measure of kinetic energy of the molecule's average kinetic energy. And kinetic energy, the equation is 1/2 mv squared. And this idea says that if you're at the same temperature, the molecules will have the same kinetic energy. But the speed of the molecules will be different. And the speed, which is velocity here, this could also be thought of as speed, is inversely proportional to the mass, which means the heavier the particle, if the mass is higher, the velocity will be lower. Or if the mass is lower, the velocity will be higher. So these are inversely related. And there's actually Graham's law, which you can use to determine the mass of a gas, molar mass of a gas, if you know its speed, how quickly it escapes, and so forth. So we're actually looking for the highest temperature. Now we have 2 high temperature here. We have 50 degrees Celsius for this flask. We have 50 degrees Celsius for this flask. So now we take a look at the type of molecules present. Here we have nitrogen. Here we have oxygen. The question is, which is heavier? Nitrogen, being diatomic, is 28 grams per mole. Oxygen, also diatomic, is 32 grams per mole. Oxygen turned out to be heavier, which means it travels slower, so nitrogen wins. So in this case, B, flask B, would be the correct answer. 7 says, which flask contains the smallest number of moles of gas? So what we'll have to look at is pressure. So first of all, this is going to be for the second part. So we can take a closer look at it. Erase that. So we're looking at the smallest number of moles. We're looking at these 2 flasks because they have the smallest pressure. Because pressure is a effect of how much gas you have. It's also an effect of temperature. So now, since their pressures are the same, we'll have to take a look at their temperatures. 50 degrees Celsius versus 40 degrees Celsius. The question is, which one of these has less moles? Now, it may not sound intuitive or logical right away, but it turns out that this one actually has less moles. The answer is also B. And here's why. If you take a look at PV equals nRT, we're looking at moles and temperature. How are moles and temperature related here through PV of nRT? Well, they are related inversely. If you increase N, T must decrease. Think of it this way, if you remove R, if you move R to the other side, you'll have to divide by R. Either way, whatever happens. Then this ratio right here, in order for it to remain the same, and if T goes up, N must come down. Another way of looking at it is, in order for this to achieve a higher temperature, it must have less moles, or rather, it's operating at a higher temperature in order to create the same amount of pressure as this flask. So the pressure is the same. In order for this to achieve the same amount of, since you have less moles here, it has to be at a higher temperature. That's another way of looking at it. All right, and number 8 says, which flask contains the sample with the greatest density? Density, remember, is all about mass over volume. Now, because they're all the same volume, and it doesn't say so, we're assuming that they're the same volume. Let's assume they're the same volume. They definitely look like they're the same volume. So density is going to be which one has the most moles of gas, because then the most moles give us the most mass, as long as the masses are comparative. And in this case, we have 2 atmospheres. Yes, this one is a little cooler than, say, this one, but the 2 atmospheres definitely double the amount of mass you have as compared to this flask. And the temperature won't, the temperature increases only by a small fraction. So C would be the answer for number 8. So think about these questions. They are a bit tricky maybe, and then we'll do a few more here on the second page. So take a look at number 12. So this goes through a little bit of calculations using math with gases. There's a lot of this sort of thing that is asked about. So we have ourselves a flask containing 1/4 mole of SO2, 1/2 mole of CH4, 1/2 mole of O2. The total pressure is 800 millimeters of mercury. What's the partial pressure of SO2? Now remember, each of these gases applies a certain pressure depending on how much of the gas there is. So you can actually, if you knew the individual pressures, the partial pressures of each of these, you can simply add the partial pressures up to give you the total pressure. And because moles and pressure are directly related, you can do the fraction of the moles multiplied by the total pressure will give you the pressure of the individual gas. And that's what we'll have to do. So essentially, let's get the mole fraction. Mole fraction is usually given as X of SO2, which will be the moles of SO2 divided by total moles. Now this will give us the fraction of SO2 over total. So in this case, we've got 0.25. Remember, this is a multiple choice question, so no calculators allowed. We have 0.5, 0.5, and 0.25 over 1.25 moles in both cases. Now we're going to multiply, this is the mole fraction, this is the fraction of the total that's just SO2. We're going to multiply this by the total pressure, which is going to be 800 millimeters of mercury. We'll have to do this calculation. Now, 0.25 over 1.25, you can think of this as 25 over 125. So if it's easier, 25 over 125, can you see that this is 1/5? This fraction is actually 1/5. So can we multiply 1/5 by 800? Can we divide 800 essentially by 5? Well, we can try to guesstimate. If this is easier for you, you know it can't be 800. You know it can't be 600 because we need 1/5 of 800. 250 is more than 1/5 of 800. You can probably cross that one out. It's going to be between these two. If you were to guess, 200 is actually 1/4 of 800. That one is still too high, correct? Because 200 is 1/4, which means, this one's out, 160 is the answer. If you're good enough to divide 800 by 5 in your head, you can probably figure out that the answer is 160, but process of elimination will get you there quicker. All right, and how about 13? If you take a look, 13 says we have a sample, 0.01 moles of gas, confined at 37 degrees Celsius and 0.216 atmospheres. What would the pressure be in the sample if it's taken to 15 degrees Celsius? Notice we're decreasing the temp and we're asking for the pressure. Now, the idea here is that pressure and temperature are directly related. So if you decrease temperature, as temperature goes down, pressure goes down. And the pressure is going to go down proportionally by the same amount the temperature goes down by. Now, temperature doesn't go down by much. Even though it looks like it goes down by more than twice, your pressure will not go down by more than twice. Because what will happen is we have to convert to Kelvin. Remember, temperature has to be used in Kelvin. So this 15 degrees Celsius is actually 87 plus 273. So we have 287 Kelvin. And for this one here, we have 310 Kelvin. So notice our temperature goes down by this factor. It goes down by a factor of 287 over 310. And if you remember, we did the ratio method. So this fraction right here will be multiplied by our pressures to see what the new pressure would be. So this gets multiplied by 0.216. And the idea is, remember we said multiply the pressure must be affected by the temperature change. Since the temperature is going down, we want to put the small number on top for the overall pressure to go down. Now, this ratio is not very big. It's pretty close to 1. I mean, it's a little less than 1. This is a multiple choice question. We cannot use the calculator. So 0.216 is going to be decreased just by a little bit. It can't be this because this is increased. It can't be this. It's increased. This is decreased by way too much. This is actually, if a person didn't account, if they just did it using temperature, you'll get this answer. So this one's out. It's between these two. And the question is, which one do you think it is? Well, this one is increased by more than this one. Our decrease is slight, so I would pick this one as the decrease. because this one is actually quite a bit more, from 216 to 175. We're decreasing more by like maybe a fifth or a fourth. So that's quite a bit more. So another guesstimation style problem. Right, how about number 14? If you take a look at number 14, it says a 2-liter container will hold about 4 grams of which of the following gases at 0 Celsius, 1 atmosphere. Now you could figure this out using PV equals nRT. This will be pretty tedious if you go to the PV nRT route. I would suggest using this definition. 1 mole of gas around standard degrees, this is STP, standard temperature and pressure, is, do you remember? 22.4 liters. So since we know this, and we have 2 liters, so we have roughly a tenth of a mole. Since you have 2 liters, 22 liters gives you 1 mole, so 2 liters gives you roughly a tenth of a mole. It's more like 1/11th, but 1/10 would be easier to work with. So then 4 grams, a tenth is 4 grams, so a whole mole, because we're asking about a mole, a whole mole is going to be about 40 grams. And if you take a look at the molar masses of these, you'll find that CO2 has a mass of 44 grams per mole, and CO2 is the one that would match. Notice 44, so it's a little bigger because we really have 1/11th of a mole. So think about that one. That one is a bit, I should say, tedious. Not tedious, but you need to know some facts. And number 15 will be a bit tedious. And let's finish up with number 15. So here we have 0.03 moles of a sample of, this is ammonium nitrate, which is placed, here it is, in a 1 liter flask, which is sealed and heated. All the ammonium nitrate decomposes. According to the equation above, the total pressure in the flask is total pressure and temperature, 400 K. At 400, okay, what is the total pressure? We're asking for the total pressure, right. We'll actually have to use PV equals nRT. PV is nRT. Now this one's going to be a little difficult, but we can probably do it. Let's try it. Since we have 0.03 moles of a gas, we know that we'll have to, let's see here. Well, we've got moles, and so our gas is actually going to be 0.03, but because we have 3 moles of gas total being produced from 1 mole of ammonium nitrate, we'll have to triple this. So we actually form 0.09 moles of gas total. That's a little bit of stoichiometry here. And now, since we have our moles, we have our temperature, we have our volume as 1, we can plug everything in to PV-nRT and solve for pressure. So rearranging it, pressure is nRT over P, over V. Let's try to plug them in. So N is 0.09, R 0.0821. Notice they give this to us in the equation, 0.82. That's good enough. And 400 our temperature, and nicely we only divide by 1, so this we don't have to worry about this. The question is, can we multiply this in our heads? Now let me show you that it's actually easier than it looks. Here's another math trick that you can use. I'm going to swing this over twice to give me 8 for the number, and I'm going to swing this over twice this way to give me 4. Notice I moved this 100 times forward, this 100 times back. I'm multiplying 8 by 4. 8 by 4 is 32, correct? And then I have to multiply by 0.09. Well, I could just probably guesstimate. Let me guesstimate. 0.09 is like 0.1, like a tenth. So I'm cutting this down to a tenth, which I get about 3. And is that one of the answers? Yes, it is. So notice we were able to do a PV-nRT problem using in our heads, which is pretty impressive. So try to do the same thing on the next question, and I'll leave you at that. I'll let you practice number 16. It's the same sort of thing, using PV-nRT in your head, and then we will answer any questions in class.